Welcome back everyone to section number 8. Again, this is Stokes' theorem. We're going to have a nice little short video here, but I'm going to kind of go over the idea of a more formal proof of Stokes' theorem. So last time we talked about the upgrade, right? How can we upgrade from Green's theorem to Stokes' theorem? But if you just wanted to prove Stokes' theorem, what would it actually take? Right? And so again, here is the statement of Stokes' theorem, all these nice conditions and everything. And so again, our idea here is that this has something to do with circulation, right? So when we do circulation on the boundary curve, C, right, that this is equal to the circulation at every single point, right? And we add all these things up, and there's a lot of cancellation, right? And kind of the only things that don't cancel are there on this boundary curve. So that's the idea behind Stokes' theorem. The first thing I want to do in order to kind of verify this, right, we should verify that curl of f actually has something to do with circulation at a particular point. So, when we originally started circulation around a point, right, we rotated things in just a plane, right, the xy plane. It was perpendicular to k. And that's how circulation started, right, in Green's theorem. And so in particular, right, since it's perpendicular to k, you may say, okay, let's go ahead and take that circulation in the xy plane and kind of make it a k component here of some vector. There's also going to be circulation in kind of these other planes. So for instance, in the xz plane, right, that's going to be perpendicular to j. And there's going to be circulation in the yz plane that's perpendicular to I. And if we want to consider all of the circulation available, right, well then we want to kind of also include these things, right? So we should do the circulation in the yz plane, and again that was perpendicular to I, and we have the circulation in the xz plane, and that was perpendicular to j. And this is somewhat, right, it's a confusing subject, so what I like to think about this, or how I like to think about this, is I think about little drones here. So at every single point, right, we're actually taking lots and lots of readings. So let me go ahead, I'm going to draw kind of these three little arms here. And let's see, something like this. And we attach to these things these little flaps. I probably will not do a good job drawing these things. Okay, so something like these, we attach these little flaps to every single point in space. All right. So it's like these pinwheels that we attach to points. And so imagine that we have some very interesting vector field, you know, a strong breeze or something like this that's specifying, you know, what maybe how forces are acting on points, right? And so originally, right, we did circulation in the xy plane. That was how much this pinwheel right here is spinning, right? Is it spinning in the counterclockwise direction? Is it spinning in the clockwise direction, right? What is that vector field? How is that vector field acting on this point? And we get circulation in the xy plane. That's all of the stuff that's perpendicular to k here. Right, so again, this is k, here would be I, and here would be j. Right, this is the x direction, the y direction, the z direction. And so this pinwheel right here is telling us information about circulation in the xy plane. Now likewise, we could ask, okay, how is this pinwheel spinning right here? How is the vector field acting on this pinwheel? Is it going in the counterclockwise direction? Is it going in the clockwise direction? What's happening, right? And this is telling us information about circulation in the yz plane. And likewise, we could ask, how is this pinwheel spinning, right? Is it staying still? Maybe there's no circulation in the xz plane. Maybe it's spinning in the positive, you know, the counterclockwise direction, or the clockwise direction, right? So again, this pinwheel right here is telling us about circulation in the xz plane. Again, here's our x direction, here's our z direction, so it's perpendicular to xz. And so I want to embed three pieces of information. I want to embed circulation in the yz plane, circulation in the xz plane, and circulation in the xy plane. Those are the three pieces of information that I want to embed in some mathematical thing. And a good mathematical thing to embed three pieces of information is, well, a vector, right? If we add them all together or something like this, right, we lose something, right? We wouldn't be able to recover, right? There's lots of ways to get 5, for instance, right? It could be 1 plus 2 plus 2. It could be 0 plus 5 plus 0, right? So we kind of want to keep these things separate so that we know exactly how much circulation there is in the YZ plane, exactly how much circulation there is in the XZ plane, exactly how much circulation there is in the XY plane, right? So we want to keep them all separate. A vector is a great way to do that. So this right here is a vector that kind of embeds all of our information about circulation. Circulation in kind of the 3 different ways that it can occur. Okay, so if that's our goal, now we need to think about, well, how do we get circulation, in the XY plane at that specific point, for instance? Well, that's a topic that we've already covered, right? Back in Green's theorem, it took a long time. We drew a lot of pictures like this, right? But we got the circulation in the XY plane at a particular point was the partial of Q with respect to X minus the partial of P with respect to Y. Now, if you do a lot more of these drawings, which I'll kind of save you from, but if you do a lot more of these things, right, we can calculate out the circulation in the XZ plane and in the YZ plane. And this is going to be the partial of P with respect to Z minus the partial of R with respect to X, then the partial of R with respect to Y minus the partial of Q with respect to Z. And so, if we want a vector that kind of talks about circulation, right? Again, we can kind of put all of these things, the circulation in the XY plane, the circulation in the XZ plane, the circulation in the YZ plane, right, into a vector. So I'm going to go ahead and put those things as the components in my vector. And we're making this mega circulation vector, right? So this is a vector that talks about circulation at points. Now, right, mega circulation vector isn't very official, but we've actually seen this vector before, right? This is exactly curl of F, right? Back in the definition, I told no one to, right, we shouldn't memorize this thing. We should only memorize that this is the del cross F sort of deal. But if you calculate that all out, this is exactly what you get. So this mega circulation vector is our curl vector. And so in fact, right, our first goal here was I wanted to say that curl has something to do with circulation, right? Curl of F has something to do with circulation. So curl is actually embedding all of this circulation information, right, as its 3 components of its vector. All right, so now our goal is, right, again, we want to talk about how much circulation is happening on a surface, right? That is our goal for the surface integral component, right? And so recall really quick, right? So 0 circulation means that there's no rotation. There's no circulation happening. If you have a plus, right, so this means circulation is happening in the counterclockwise direction. If you have negative, minus, this means that we have circulation in the clockwise direction. And right, we want a number at the end of the day to say kind of overall, is there more circulation happening in the positive direction, aka the counterclockwise direction, or is there more circulation happening in the negative direction? Right, so I want to add up all of the circulation over the entire surface. So that means I need to add up numbers, right? It doesn't really make sense to add up vectors in this case. And so I need to turn this mega circulation vector into a number. And the claim is, well, in order to do this, we can realize that there's some directions that we don't particularly care about so much, right? Because whatever's pushing this, whether it be water or beads or particles, right? Whatever's circulating, right? Something's got to be circulating. I'm talking about whether it's blood maybe or something, right? So it's got to be drops of water or beads or particles, right? Something here is circulating. But they're circulating on the surface, right? So there's some directions that I really don't care about, right? If there's any circulation happening in those directions, because again, these things are kind of stuck on the surface. So for instance, if I go ahead and draw maybe a nice surface over here, something like this. So here's my nice surface. Okay. And the claim is if I want to know how is the circulation happening at this point right here, well, I don't care at all about in the normal direction, right? So if I go ahead and maybe draw out my favorite normal vector right here, the particles aren't jumping off the surface. Again, I'm calculating the circulation on the surface. So really the question is, how are the particles, how are these beads, how are, whatever's circulating, how are they going around this normal vector? Because they're not coming, off the surface. So it's really just how are they going around this normal vector? Okay. And so with using that, I can go ahead and kind of get rid of the parts of the circulation vector that I don't particularly care about at this time. And so the circulation at the point on this surface will be the curl of f, but then only dot with the normal vector here. And that will give me circulation at the point, but only those things that are on the surface, right? Only the circulation that's on the surface. So again, quick reminder here, right? N is the unit normal vector. The surface tangent plane at the point, and we see now that curl of f dot n will give us the amount of circulation that's happening at that point. So now we can use the similar argument to Green's theorem, right, where we broke the surface up into lots and lots of pieces, and we can say that the surface around the boundary of S is going to be the same as the circulation around each point in S, right? If we add all these things up, there's a lot of cancellation that happens in this case. And so we're going to get the line integral, and if we calculate out circulation around the boundary, this is going to be equal to if we summed up the circulation on the surface, right? So, and the circulation around each point of the surface, well, that's what we did all this work for. That is curl, oops, I forgot my L up here, curl of f dot n. So that is the circulation at each particular point, and that is why Stokes' theorem is the way it is, right? When you ask, okay, why is it this way, right? You really have to think about the proof for these things. All right, so hopefully this has given you a little bit better understanding about why Stokes' theorem, right, is the way it is. In class, we'll be doing some more applications, some more problems to get some practice actually applying it. All right, I'll see you then.